This is Adel Gastli. I'm going to present to you part 4 of the chapter about induction machines. In this part, I will present the performance characteristics and operation of induction motors. This will include the power flow inside the machine, the torque and speed characteristics, and the different modes of operation. The power flow inside the induction motor can be described as follows. The input is an electric power and designated by Pin. The first losses are the stator copper losses designated by PCU1 and the core losses P core. Then the remaining power is the air gap power designated by PAG, which passes through the stator to the rotor through magnetic coupling. Inside the rotor, the power loss are the rotor copper losses designated by PCU2. The remaining power will be converted into mechanical power designated by PDV for developed through electromechanical energy conversion principle. Then there are mechanical rotational losses designated by PROT, which are due to bearing, friction, and windage. Windage means that when the rotor is rotating at high speed, there is a friction with the wind that creates an opposite torque trying to slow down the rotor. These are mechanical losses also. Finally, the remaining power that is received by the mechanical load is the output power P out. So the efficiency of the machine is the ratio of the output power received by the mechanical load over the input power consumed by the motor from the electric source. Using the equivalent circuit, we can find the expressions of the power flow inside the induction motor as follows. The input power is the three-phase power, is Pin, and is given by this equation. The stator copper losses are given by this equation. The core loss is determined by this equation. The air gap power is determined as shown by this equation. The rotor copper losses are determined by this equation. The developed power is determined using this equation. Then finally, the output power can be determined using these equations. Notice that most of these equations require the knowledge of the slip and the rotor current I'2 refer to the stator side. The stator and rotor currents can be calculated using the set of equations derived from this equivalent circuit. Start by determining the equivalent impedance. So we first find the equivalent parallel branch Zm as given by this equation. Then the parallel connection of Zm with the rotor impedance leads to this impedance Z2. Finally, the total equivalent impedance Z equivalent is calculated using this equation. After calculating the total equivalent impedance, we can calculate the stator current as V1 over Z equivalent. Then we can calculate the back EMF E1 using KVL as shown by this equation. Finally, we can calculate the rotor current referred to the stator as I'2 equal E1 over the rotor impedance. So after calculating the stator and rotor currents, it is possible to calculate all other characteristics and variables of the induction machine, being a torque, power, or efficiency. Of course, these calculations require the preliminary knowledge of the slip. Let us see more in details the set of equations which are used to determine the power flow inside the rotor of the induction machine. Since the air gap power is the total power that is transferred from the stator circuit to the rotor circuit, it is also the electric power consumed by the total rotor resistance R'2 over S. So we can express it as PAG is equal 3I' square multiplied by R'2 divided by S, the slip. The total copper loss inside the rotor resistance R prime 2 is determined as 3 times I prime 2 square multiplied by the rotor resistance R prime 2, which is also equivalent to S multiplied by the air gap power. Now the developed power is the power inside this resistance. Thus, it is equivalent to 3 R prime 2 R prime 2 multiplied by 1 minus S divided by S. Notice that it is also equal to 1 minus S multiplied by the air gap power. This electric power is converted into mechanical power through electromechanical energy conversion principle that is equal to the developed torque times the motor speed omega m. Considering that the synchronous speed is equal to the motor speed over 1 minus S, we can also write that the air gap power is also equal to the developed torque times the synchronous speed in radian per second. So from this set of equations, we can describe the relation between the air gap power, copper loss, and developed power as function of the air gap power as 1 S and 1 minus S. And the developed torque can be calculated from the air gap power as P air gap over synchronous speed or developed power over motor speed. These equations are very useful and helpful in simplifying the calculations of the power and the efficiency of the induction machine. For simplicity, the IEEE equivalent circuit is usually used where the core loss resistance is omitted and the core loss are added to the rotational losses during the calculations of the efficiency. The total equivalent circuit impedance is calculated as shown here. The step-by-step procedure for finding the performance characteristics of the induction machine will be listed in the next slide. So the first step is to find the total equivalent impedance. Of course, in here, the slip should be first known. The second one is to find the stator current. So the stator current is determined as the ratio of V1 over Z equivalent, which is equal to the amplitude of I1 with the phase angle phi. So this angle can be used to find in the next step, the third step, the power factor at the input. Then in the fourth step, we can find the input power. After that, we can find the stator copper loss, then the air gap power. Then we find the rotor copper loss, then the developed power and torque, and finally the output power and torque. All these steps can be followed whenever we want to find the operating characteristic of an induction motor. Of course, we should know the slip and the rotational losses and the frequency of the supply and the voltage applied to the motor. All other variables can be easily determined following these steps. Now, to find the torque speed characteristic, we will use the gamma type simplified or approximate equivalent circuit. From this circuit, we can deduce the expression of the rotor current referred to the stator side using this equation. We know already from the previous slide that the developed torque equation is as shown here. Thus, replacing the rotor current by its above expression, we can find the torque as a function of the synchronous speed and slip as shown here. Using this torque equation and varying the slip from 1 to 0, which is equivalent to varying the motor speed from 0 at standstill up to synchronous speed, which is the ideal no-load condition, we can plot the torque versus speed characteristic as shown here. So if we start an induction motor at ideal no-load condition the machine torque will start from the starting torque value TST. It will then increase until it reaches its maximum torque value at a certain slip Smax. Then it will decrease to 0 when the motor speed reaches the synchronous speed Ns, which is equivalent to 0 slip value. So this region of the torque speed characteristic between the starting torque and maximum torque is called large slip region. And the region between the maximum torque and 0 torque is called the small slip region. So Smax here is not the maximum slip. The maximum slip is 1. However, Smax designates the slip at maximum torque. The starting torque and the maximum torque are very special operating points of the induction motor torque speed characteristic, which are very important to know. We will see how we can calculate them in the next few slides. Now let us find the expression of the maximum torque. As you know, mathematically, a maximum of a function is calculated by taking the derivative of the function and setting it to 0. This is what we will do with the torque equation. So we take the partial derivative of the torque function with regards to the slip, we set it equal to 0, and then we determine the value of the slip that satisfies this condition. I let you do this exercise yourself and try to find this expression of Smax, which is the slip at maximum torque. Now, replacing S by Smax that we just found in the above equation of the torque will give us the expression of the maximum torque Tmax as shown here. Notice that Tmax is not a function of the rotor resistance, but is proportional to the square of the stator voltage and inverse proportional to the synchronous speed. Usually, R1 is very small compared to X equivalent, which leads to conclude that the maximum torque is proportional to the square of the ratio of the voltage and the supply frequency. Now, this square of the frequency is coming from the product of the synchronous speed and the equivalent reactance, which include the frequency also. So you can notice that if we keep the ratio V1 over F constant, and you vary V and F, then we can maintain a maximum torque at a constant value. Now we can determine the expression of the starting torque by considering the fact that at starting the speed is 0, so the slip is equal to unity. So by setting S equal to 1 in the above equation of the torque, we can derive the starting torque equation as shown here. Notice that the starting torque is a function of the stator voltage and the frequency and stator and rotor resistances. It is usually desirable to have a high starting torque in order to start the motor fast. So to increase the starting torque, we can increase the voltage or the rotor resistance or decrease the supply frequency. So up to now, we have seen how we can determine the torque speed characteristics by calculating the maximum torque and the starting torque using the IEEE recommended equivalent circuit. Next, we are going to see how we can also find the torque speed characteristics of the induction motor using its Thevenin equivalent circuit. According to the Thevenin equivalent circuit, the rotor current is determined by this equation. Now, considering the same equation of the developed torque as a function of the rotor current and replacing the rotor current by its expression given above, we can find the expression of the developed torque as shown by this equation. So this is the general equation of the developed torque based on the parameters of the Thevenin equivalent circuit. We can proceed similarly to what we have done for the IEEE equivalent circuit and find the starting and maximum torques of the torque speed characteristic. So the starting torque expression can be determined from the previous expression after setting the slip to unity, as given by this equation. And similarly to the previous analysis, we can find the expressions of the slip at maximum torque, Smax, and the maximum torque by setting to 0 the partial derivative of the torque equation with regard to the slip. So as you can notice, we have obtained two equations that are function of the equivalent circuit parameters based on the Thevenin equivalent circuit. Taking into account some considerations regarding the equivalent circuit parameters, we can further simplify these equations as we'll see in the next slide. Usually, the Thevenin resistance is considered very small compared to the sum of the reactances, so our Thevenin may be neglected. So the equations of the maximum torque and slip at maximum torque can be simplified as shown here. Now, if we take the ratio between the maximum torque and the torque developed at any speed, we can get this equation. Replacing x Thevenin plus x prime 2 by r prime 2 over s max from the above equation, we can rewrite this torque ratio equation as shown here. After simplifications, we can obtain this equation, which relates the torque and slip at any operating point to the maximum torque and slip at maximum torque. Note that this is a very useful equation that can simplify a lot the calculations of the torque if the maximum conditions is known without going through a complex torque equation and calculations. As we have noted earlier, the maximum torque is independent from the rotor resistance. However, the value of the rotor resistance determines the slip at which the maximum torque will occur. So in order to start the induction motor fast, we need to increase its starting torque. To get a maximum torque at starting, we need to satisfy this relation between the rotor resistance and the reactances. This equation is obtained by setting S max equal 1 in the above equation. So in order to start the induction motor at maximum torque, we need to have r prime 2 is equal to x Thevenin plus x prime 2. This can be achieved with wound rotor type machines where external rotor resistance can be connected and used for controlling and adjusting the total equivalent rotor resistance. We will come back to this issue of starting of induction machine in the next part of this chapter. Now, let us analyze the different modes of operation of the induction machine. The induction machine can be operated in three different modes: motoring, generating, and plugging modes. To illustrate these three modes of operation, we will consider an induction machine mechanically coupled to a DC machine through a shaft as shown in this figure. These two machines combination will allow us to operate the induction machine in these three modes of operation. During the motoring operation, the synchronous speed of the induction motor is higher than the speed of the shaft, which gives a positive slip ranging between 0 and 1. In this case, the DC machine is acting as the mechanical load that is receiving its mechanical input from the induction motor. If the DC machine is controlled as a motor or a prime mover that drives the induction machine at a speed above its synchronous speed, then the induction machine will operate in its generating mode with negative slip values. Now suppose that the induction machine is running in motoring mode and all of a sudden we reverse this synchronous speed rotation by exchanging two terminals of the induction machine. The synchronous speed will rotate in opposite direction of the motor speeds, which makes the slip bigger or higher than unity. This is the plugging mode of operation. These three modes can be illustrated on the torque speed characteristics as shown in the bottom figure. In summary, we describe the torque speed characteristic and operation of the induction machine as illustrated in this figure. Note that the large slip region with positive slope is an unstable operation region, while small slip region with negative slope is a stable operation region. To explain this stability issue, we will consider that the motor is initially operating at point 1. If the load torque increases further till the maximum torque value, the speed of the motor will decrease and the slip will increase until Smax. The new operating point will move to position 2. Now, if the load torque increases further, the speed will decrease further, but motor slip cannot go beyond the maximum torque value and decreases, say, to point 3. But normally the torque must increase to satisfy the load demand. So the speed further decreases and slip will further increase. Again, the torque decreases while it should increase to satisfy the torque load demand. Hence, the speed further drops. Eventually, motor comes to standstill condition. Therefore, we have demonstrated that the motor cannot continue to rotate at any point in this high slip region. Hence, this region is called unstable region of operation. Note that the maximum torque is also called the breakdown torque. It is the maximum torque that the induction machine can deliver or produce under certain operating condition. Therefore, we should be careful not to use any induction motor with a load that requires higher torque than the breakdown torque of the motor. Otherwise, the machine cannot drive the load. This is the end of this part. Thank you for watching this video.